Today we're pleased to welcome Sergei Gukov, who's going to give us a talk entitled From Ramanujan to Rokhlin via Quantum Groups.
Yes, thank you very much for having me. It's a great pleasure to be back in Cambridge, even if virtually, in this simulated nice world. Hopefully everybody had a nice long weekend. So let me try to share again the screen and I'll get right into the talk. So here we go. So I'm going to tell you a story, and even though there is a very specific mathematical message in the story, and I may even get a little bit more technical toward the end, I want to make sure that there is yet another message which is not lost in the details of this talk. And this bigger message is about collaboration between different areas of mathematics. So this talk itself is an illustration of crossing bridges and borders from one area to another, from topology, numerative geometry, quantum groups, and so on. And this talk actually would not have been possible without this collaboration and crossing borders. So it's mathematics without borders, I guess. That could be another subtitle for this talk. So when Brian Greene had to give a math colloquium, he started with a definition. And definition was that a conformal field theory is a table of integrals. So I thought I knew what conformal field theory is, but it took me a few minutes to ponder and process this definition. I'm not sure I would give the same definition. In fact, I'm sure I wouldn't give the same definition. But the reason I want to mention this amusing fact here is if you're ever lost in my talk, think that this talk is just about table of integrals. I'm not joking. It's supposed to be broad audience expository talk. So I will be talking about table of integrals, just like going back to our undergraduate studies. And in fact, the first part of the talk will be just at the level of calculus, nothing terribly fancy. So I hope to make it accessible to everybody. So the integrals we're going to consider will be labeled by graphs. So for every graph with vertices labeled by integers, we'll have an integral to do. So it's a huge table of integrals, in fact, infinite table of integrals, because there are, of course, as many labeled such graphs as stars in the sky or fish in the sea. For each vertex in the graph, there will be integration variable. So there will be an integral to do. For instance, what's shown here will produce for us an integral in this big table, which is going to be multiple integral with 9 integrations to perform. Well, pretty big integral, but still, again, it's not going to be too far away from typical multivariable calculus. So the input data for table of integrals will be set of vertices, edges, and this integer decorations on the vertices. The same data can be conveniently packaged into adjacency metrics. Basically, it's the metrics of size, the dimension of the graph. And for every 2 vertices connected by an edge, in a slot ij we'll put 1. If they're not connected, we'll put 0. And on a diagonal where we could be a little frustrated what to do with vertex being connected to itself, we'll actually put that same integer decoration that I call AI, that labels the vertex. So to tell you what kind of integrals we're going to have, I need to give you several pieces of data. First of all, tell you for each vertex, there is integration variable, and I have to say along which contour we're integrating that complex variable. I'll call this variables xi or xj, and I'll address that question right away. We'll be integrating on a unit circle. And then the rest of the data I have to provide is the integrand, namely what we'll be integrating. And this integrand will be made out of basic building blocks, just like Lego blocks, associated to vertices and edges. And the rule will be very universal, that for every edge, we'll associate piece of the integrand that depends on 2 variables for 2 vertices that it touches. And similarly, for each vertex in this variable x that's going to be integrated over, there is a universal piece of the integrand that depends on that variable, and also the integer decoration that we call a. So here is this set of rules. And also you may notice that a new variable that has not shown up so far, variable q, appears on this slide. So it appears as part of the integrand associated to a vertex in a rather simple way, here just overall power of q, but it also enters the theta function that I sneak into the integral. And since we have a bilinear form q that we defined on a previous slide, naturally associated to it is a lattice with a symmetric form, and the corresponding theta function is what I'm going to put as part of the integrand. So these are rules, and that's it. That's actually the table of integrals that I'll be discussing whole hour. Again, it will be decorated and will get a little bit more advanced at various stages, but in bare bones, that's really what it's going to be. So I want to introduce to you this table of integrals, and then just like child learns to walk or talk, we'll ask, okay, so what kind of object is this? What kind of table of integrals is this? To which area in mathematics does it belong? So these are kind of questions that we're going to ask.
Right. Can I just, I'm already kind of confused. I mean,
Yes, please.
the third line there, the ZB hat Q, is that meant to be like made out of the previous information? But then I don't see theta there. Or is it like a new thing or?
Right, so the ZBQ is the object that we're going to discuss. This is going to be table of integrals. Again, for each vertex, there will be one integration variable xj integrated over unit circle. For each, and then integrand will be product of three factors. First of all, it will be product over vertices of first line, product over edges of the second line, and theta function in the end.
Okay, all right, good, thank you.
Thank you for the question. By the way, feel free to interrupt me at every point if something is not clear, especially about this first part. Like I say, this is supposed to be really accessible to everyone, including all undergraduates, level of calculus. That's the motto.
Sorry, as long as you're doing it this way, not via chat, I'm getting worried. Besides our undergraduates already losing it at complex integrals, what happened? Should I be worried about zeros in the denominator? So like if x sub I is 1 or minus 1?
Not at this stage. So if there is ever a pole that on our integration contour, think about principal value integral, but so I can rephrase it in several different ways where this is not going to be a concern. I can go into details, but for this expository talk, I'd probably rather skip this. But it's not a concern. We can easily discuss this. Yes.
And what was the lattice again?
The lattice, so it's quadratic form. So it's z to the number of vertices, and quadratic form is given by the adjacency matrix of this graph.
Okay. No issue. Oh, now you're assuming Q is negative definite.
Yeah.
Okay, I was going to ask.
Sorry, I didn't make it to the next slide, and I feel that some of the questions that I'm getting now actually could be easily answered by advancing to this next slide, where I say that the way I presented it as if I'm building it from basic building blocks, but of course, to that same data, I can more conveniently package information, same information, it's not the different integral, on the previous slide in the form of a more compact integrand, now just product over vertices. I didn't even have to worry about edges because it's factorizable. And yes, here I do assume that Q is definite. For whatever reason I choose negative sign. It's not important whichever sign it is, but what is important is that I want certain convergence properties later for which this definiteness will of course help. So.
And do you want B to be an integral vector?
Yes, so B here is in the cokernel of Q, this quadratic form. Yeah, so if Q is not unimodular, we have a couple of choices. Well, as many as the cardinality of cokernel of Q. And for now, maybe this is not the main aspect of this object I want you to focus on, but I'll come back to this later. And in the last part of my talk, if there is enough time, this will be the star of the show. But for now, pretend that Q is unimodular, for instance. And let's ask what this table of integrals representing. Any other questions? So that's the definition. So now, like I said, I want you to think about this long infinite table of integrals labeled by these decorated graphs as new object or class of functions. So a natural question is, what is this class of function? Where does it belong and what does it look like? So the right or one way to start answering this question slowly as we meet a new person, we ask some very basic information, where you're from, what do you like, and so on. So we'll start exploring this table of integrals slowly and gradually. So now I'll do something a little bit risky. I have done it before, but every time I try to repeat it, I get a little nervous. So I'll share with you a small mathematical file which does exactly that. So these integrals are pretty simple. There are several ways to present them. In fact, that could address some of the questions about principal value and so on. But this is a short mathematical file which basically does exactly that. So this is to illustrate that A, they're extremely well defined, and B, easy to compute. So the whole file itself consists of, first of all, input data definition. So this is where I enter the data of the graph. Then it checks, shows me some basic data such as eigenvalues of this adjacency matrix and so on. This is an actual calculation, next page. And finally, there is an output. So let me run it for you for this specific graph. So this is a graph with 4 vertices. So naively, it seems that this is an integral of multiplicity 4 that we'll be doing. And let me just evaluate this notebook. So it's very quick, very concrete. It's running in real time. And here it is. Here is the output. So variables x, which were assigned to every vertex, got integrated out, so we don't see them anymore. That's normal. But there was this variable q that entered theta function and also various factors, which remains, and what we get is a q series, which up to overall power of q has integer powers and integer coefficients. So that's the first thing we observe by doing this sort of integral. Okay, so I'm going to take this answer and save it, copy for the rest of the demonstration. And I'll ask Mathematica to forget everything that just happened. And then I'm gonna change the graph. So now I want to ask a question, how does it depend on this graph? So what it would look like for a slightly different graph. For instance, if I put here 8, 1, namely increase the number of vertices, make now a graph with 5 vertices labeled in a completely different way, what would be the outcome? So let's ask Mathematica to do this computation. And like I say, I'm always nervous when I do this in real time, this sort of demonstration. So first, let me check that everything makes sense. Sometimes I make mistakes. So here is the graph, it's connected. I didn't mess anything up on the code. We can check that it's still negative definite. That's an assumption that we're gonna relax later, but for now we wanna keep it. And now scrolling all the way to the bottom, what we see is that the output of the calculation here is exactly the same answer as it was before. So I changed the graph, I changed some of the labeling, but it didn't change the answer. And therefore, what happens is that we defined a function or class of functions associated not quite to the graphs, but rather to equivalence classes of the graphs, equivalence classes under certain relations. That's what we just saw. And these relations, surprisingly, one can find in a textbook on topology of 4 manifolds and 3 manifolds, for example, on Kirby calculus. And the joke here is that we started with calculus and got to Kirby calculus. In fact, when Mike Friedman saw a version of this talk, he quickly remarked that this is perhaps one of the quickest way to learn about Kirby calculus or Kirby moves from a table of integrals. More specifically, these are actually Neumann moves introduced by Walter Neumann that are special instances of Kirby moves, which in topology represent different equivalent ways of building the same three-manifold from cutting and gluing techniques. So the graphs in that context are called plumbing graphs, and these operations, various generalizations of blow up and blow down operations, here illustrated for a couple of moves. There are a couple of more that I'm not listing, but the list of such moves is very compact. There are about 4 or 5 of them total, very much like Reidemeister moves in the world of knots. So the utility of these knots in topology is something I'm going to comment on later. But for now, I want to formalize the statement that we saw with our own eyes, that this table of integrals is actually invariant under this set of moves. So that's a statement that's not too hard to check from the definition of these integrals. And for now, let's assume that Q is negative definite. Again, I'm going to relax this condition later. So the statement first appeared in our joint work with Pavel Putrov, Komorn-Waffe, and Dupay. And over the years, first some assumptions were relaxed. I'll comment on this as we go. And also some steps were improved and streamlined. But basically, the statement is that in this universe of, say, negative definite graphs, one finds invariants under this Kirby-Neumann moves, which are valued in Q series with integer coefficients, integer up to overall power of Q. And not only we get just a single Q series, we get a collection of such labeled bulk kernel of the adjacency matrix. And if you ask what is the meaning of this kernel in the three-manifold that the graph defines, it's actually first homology of the three-manifold. And as a set, that's the same as the set of spin C structures on three-manifold. If you like spin C structures, that's what I want you to think of. If you don't like spin C structures, think about it as a bunch of functions labeled by elements of H1 of the three-manifold. So these two sets are isomorphic, but not canonically. And again, if I have time, I'll come back to this in the end of the talk. It's not hard to check that this series is always convergent inside the unit disk, but not on the boundary. And you can even run a very simple ratio test for the coefficients, which are growing very slowly. So that's part of the reason that it's converging pretty well. So we started with a table of integrals, and now we learned that it's something that makes sense in the world of three manifolds. Namely, if you want to define an invariant of a three manifold, you want to assign to any construction of a three manifold something. In this case, it's a Q series or other collection of such, and check that it's invariant under equivalences that represent different equivalent ways of building the same three manifold. So it's by definition or by construction, according to this theorem, an invariant of, in this case, plumb three manifolds. And one of the questions, obvious questions, is, have we seen this invariant before? What kind of invariant is this, or how it's related to other known invariants of three manifolds? So good news and bad news is that until recently, there were no other Q-series valued invariants of arbitrary closed three manifolds. So it is not something we can compare to. But if we take Q to various limiting values, for example, to roots of unity, then it will actually relate to something that we have seen before. So that's what makes it interesting. And now I have to tell you the real story. So this was more of amusing introduction, but now I have to confess how this all came about. And the real problem that we were trying to solve is a problem that has about 25-year history, goes back to very visionary work of Louis Crane and Igor Frankel, who suggested that the world of quantum group invariants should admit a lift, homological lift categorification. A few years later, a former student of Igor Frankl, Misha Hovanov, beautifully solved this problem for the Jones polynomial, which has integer coefficients and, as we now know, can be represented as graded Euler characteristic of homology associated to a knot. And since knots and three manifolds share the same world, and quantum group invariants of knots and three manifolds are part of the same package that we usually call a set of Wheatland-Reshetikhin-Turaev invariants, then it's natural to ask and expect that the same should be true for invariants of knots inside general three manifolds. And that's actually the problem that we were trying to solve. So this is a pretty challenging problem, and it's easier said than done. In fact, if you start making even initial first steps, you quickly encounter the following obstacle. The Jones polynomial of any knot, or in fact, any quantum group invariant of knots and links, has naturally integer coefficients when written in terms of variable q. Exponential of 2 pi over integer that characterizes the root of unity. So here q is a root of unity. But for three manifolds, these invariants are not polynomials or power series or anything in terms of q. They're written in terms of this order of the root of unity that I call k. And the slide illustrates very concrete expression for WRT invariants of a very simple class of three manifolds. You can probably even guess what it is. But the point here is that k does not enter as part of the exponential. It's not written in terms of q. It enters as upper limit of the sum or prefactor. So if you try to write this prefactor in terms of q, you'll get something like log q to a certain power. That doesn't look like power series with integer coefficients at all. So that's actually a major challenge, and you encounter it basically at step 0. And various people have thought about overcoming this challenge. And some ideas listed here involve Hopfological algebra, which is an interesting mix of Hopf algebras and homological algebra introduced by Hovanov and studied by several other people. This approach is trying to resolve this issue by working directly at the root of unity. Another approach, which also works directly at the root of unity, pioneered by Raphael Rouquier and others, involves high representation theory. And as you can probably guess in this talk, I'll follow yet another approach where these values at roots of unity have no integrality. They obviously show no obvious sign of integer coefficients, but they appear as limiting values of some power series in Q, which in turn has integer coefficients. And then one can try to categorify those integer coefficients, realize those integers as graded Euler characteristics. So that's the subject of this talk. However, in trying to pursue this route, one of the surprises was that indeed everything seems to work exactly the way we plan, but we get not a single Q-series. In this talk, I'll say very little about such categorification, even though this is definitely motivation and the goal. I'll just focus on the Q-series itself. And it comes not as a single Q-series for a given three manifold, but it comes as a collection of such labeled by these labels B, which take values either in first homology or set of spin C structures. So this was a surprise because first of all, it was completely unexpected based on some initial steps in late 90s, early 2000s. And then there was a second turn in the story when it was realized that this set of labels should actually be viewed as a set of spin C structures. And this is even more striking and surprising. Like I say, these two sets are isomorphic, but not canonically, and I'll come back to this later. But spin C structure is basically a lift of a spin structure on a three manifold. And the reason it's surprising is that the definition of WRT invariants of Reshetikhin, Turaev, and Witten does not actually require a choice of spin structure anywhere. in TQFT jargon, it's not a spin TQFT. So therefore, it's really strange that when we try to categorify or solve this problem of Crane and Frankel, one needs to introduce not only spin structure, but its leaf to spin C structure. It's not a contradiction, because if one tries to recover WRT invariance from this Q series, one first of all takes a limit where Q goes to root of unity. That's perhaps not too unexpected. But we also sum over this extra data. We sum over a label B with certain universal coefficients, which you can easily find in papers listed here, or I can explain later. So these coefficients are pretty simple, but the point is we're summing over this additional data, so there is no contradiction, but still it's a little unexpected, or it was back in those days, about a few years ago. And I have to admit that I myself was actually very skeptical of what's going on here, and did not view this as only intermediate step in the development until more and more evidence accumulated, and this labeling by spin C structures became clear from several different perspectives. And I'll try to share with you some of these perspectives in a slightly more technical part toward the end. But from this point on, I'll go back to asking a question: what kind of object is this Z hat labeled by this labels B? So now we see that it may play some role in topology. I hope I explained to you what kind of problem it is trying to solve. And next question is, okay, how do we construct it? And what kind of Q series is this? Any questions at this point?
Did you make any connection until now of the actual structure of the graph and the three manifold?
No, not yet, but I'm about to do it. Thank you, Barry. So yes, let's address exactly this question. What's the relation? Or I'm not going to be able to provide full details, because that's why you should definitely take a topology course. But so I encourage all the young people on this call. But I'll say a few words at least, indeed, what's the link between the graphs and general three manifolds. And this will be also important for generalizing this invariance to arbitrary three manifolds. So every three manifold, closed oriented three manifold, can be performed or can be built by performing an integral Dane surgery on a knot or a link. So this is the content of this famous theorem by Licorice and Wallace. And according to this theorem, we should think of, for example, a three torus not as a Cartesian product of three circles, but rather as a result of excavating tubular neighborhoods of Borromean link components and gluing them back with a twist. So in this way, claim is that if we do this operation on any knot or link, we'll recover any three manifold in the world. And equivalences of this construction are precisely those Kirby moves that I alluded to earlier. Now, for a very special class of links, namely those which are built out of collections of unknots, we can simplify the data, and instead of drawing the link itself, we can substitute every unknot by vertex. Every time they're linked, as in a Hopf link, we draw an edge, and voila, this is the graph that we saw earlier. So from the point of view of three manifolds, this set of graphs actually is describing a rather small universe of three manifolds. It's still big, it's still infinite and so on, but this illustrates what you want to do if you want to extend what we saw earlier, this table of integrals, to really arbitrary three manifolds. So from the viewpoint of topology, the challenge is now to extend this definition I showed you to arbitrary links and knots. So for instance, I may wish to replace one of the unknots in the graph shown here by a copy of a non-trivial knot that now is knotted with itself. So
question, it looks like if your graph has loops in it, then there's a twist ambiguity in how the necklace comes around to itself.
Yes, that's an excellent question. So indeed, another assumption we may want to make from in the beginning is to not allow loops, but actually loops can be allowed and are okay. So I'll be happy to come back to it a little later. So nothing goes wrong with the integral, actually. So the integrals that I'm showing you are perfectly fine. So they can handle these loops perfectly well, especially if you still make this assumption of definiteness. But something interesting happens, and this is related to this choice of spin C structures, that whenever we have a loop, we have now more spin C structures or these additional labels associated to the loop. So that's actually where loops become delicate. And if you allow me, I want to relegate this till the end, because this is, again, to me, more juicy, but also more technical part of the material. But that's a great question. Yes. Yes. So, right. So suppose we want to do something less ambitious and just keep one of these graphs with, I don't know, a dozen vertices, but replace one of the components by a non-trivial knot. Turning it into now more and more general link. So as you could have guessed, what's going to happen is that only part of the integrand that depends on that variable xi that we're changing is going to be modified. So now the question becomes, how do you find this integrand? Or more generally, how do we find integrand for general knot or link complement? So if we succeed in that, then according to this general theorem, and if we manage to show that it's invariant under Turby moves, then we basically define it for general closed three manifold. So that's the problem that we tried to tackle with Ciprian Manolescu, and to a certain extent succeeded. So we developed a method that in principle can be applied to every knot or link, how to construct this, this integrand. But it's extremely inefficient and is using composition of resurgent analysis and recursion. And in practice, we were able to implement this only for torus knots and only one hyperbolic knot. After a month of work, we did this figure 8 knot. So it was kind of promising, but not good enough to prove general statements about such surgeries. So we didn't know what to make of it. In a sense, it's encouraging that it's providing lots of examples and there is no conceptual obstacle, but it's just inefficient. So then I can't resist to not advertise work of my own student who found a much better approach shortly after using R matrices. So here the problem is reduced to knot and link complements. So, or in other words, to knots and links. And this fellow, Sang-Yuk Park, found a clever way to construct such integrands for knots and links using R matrix of a quantum group at a generic value of Q. So that's of course very natural because we're trying to move away from roots of unity and construct Q series, which depends on Q inside the unit disk. Unlike construction of Rishi-Tikhon and Turaev, this uses not finite dimensional representations of the quantum group, but rather infinite dimensional Verma modules. That's also natural because these variables X that appear, actually, I skipped one part, so maybe I should have pointed out here that, for example, for knot complement, the set of spin C structures or H1 is Z. So it's natural to package all this invariance labeled by this H1 elements in a generating function. So that's the role of this variable X. It's basically dual to the choice of H1 element or spin C structure. And that's the integrand. That's demystifying what we're integrating over in this formula. And this is the variable that's basically complex highest weight of a Verma module in this R matrix approach. And this is very efficient. So I told you that with Ciprian, we managed to produce only one hyperbolic knot after a month of work. That was figure 8 knot. Using this R matrix approach, he managed to knock down many knots and links up to 10 crossings, many infinite families, positive braid knots, homogeneous knots, some classes of fibered knots, and so on. So here is a show-off example of a 10 crossing knot for which +5 surgery has H1 Z5, and therefore there are 5 Q series invariants, which again have the same general structure as what we saw in the demonstration based on graphs in a simpler version of the table of integrals that I showed you a few minutes ago. So now this story is developing even further. So this was about a year ago, and this bright student is going to be on the job market in the fall. So that's part of the reason I want to mention his name. So from now this looks way more promising than approach we had with Cyprian, and again, several other techniques are becoming available. So if you have in mind the three manifold, which is surgery on some knot or link up to 10 crossings, now very little is stopping us from producing the answer. So that's looking promising. So this is the right time to start thinking about general statements. But I want to now look at this table of integrals from yet another point of view. And when I was young, I learned that a general broad audience talk, colloquium style talk, should have at least one joke, and I made an attempt of making one in the very beginning, at least one theorem, and I showed you one theorem about plumbing graphs, and a couple more will come in a minute, and at least one example. So this is going to be same example, in fact, same exact example I showed you using Mathematica code, but now computed in a different way. Now computed via integrand associated to either trefoil knot or figure-8 knot. It's actually same manifold as the plumbing graph with 4 vertices that I had in Mathematica file, and this could be viewed as yet another check that yes, under Kirby moves we get the same number or the same invariance. So it first of all proves topological invariance. But now I want to take a look in this simpler example at what kind of Q series is this. So ask about Q dependence. So here, in fact, I give you two answers, one for three manifold itself that we saw before, and another for its reversal orientation cousin, a manifold with opposite orientation. And again, using this integrands, even the ones that we had with Cyprian, like I say, we did have the answer for trefoil and figure-8. You can quickly compute this Q series. In this case, it's a homology sphere. There is only one Q series. There is no H1 to worry about. So therefore, in each case, you get one Q series. And amusing fact, once we're trying to explore what kind of object it is to notice that these two answers for the original manifold and for minus this manifold are actually related. So I invite you to do the following simple exercise that one can do on the back of the envelope. Take any of these functions, say this one on top, replace Q by its inverse, and then try to rewrite the answer in terms of Q. So basically multiply by sufficiently large powers so that the numerator and denominator again look like they're written in terms of Q. What you're going to get is the one on the bottom and vice versa. So this particular function that presents the answer for this manifold shows that it's a Q hypergeometric function that defines for us the answer of a manifold inside the unit disk, defines the answer for manifold with opposite orientation outside of the unit disk in the Q plane. But of course, it's not convergent on a unit circle itself. So that's an amusing fact. That's something I want you to keep in mind for the next couple of minutes. Another fact you find is that it's one of the functions, exactly this one I just showed you, that appeared in the letter of Ramanujan to Hardy a little over 100 years ago. In his last letter to Hardy, Ramanujan wrote 17 examples of Q series of functions that to him were very magical and nice, and he couldn't really characterize it in modern mathematical terms to what class they belong, but he definitely was onto something and tried to explain this in the letter. And the example that appears here is actually one of the 17. Of course, this is just an accident because I could have picked many other millions of graphs in my illustration and I would miss his 17 examples, but let's carry on with this a little bit. And what Ramanujan pointed out is that these objects are not quite modular if now we put on a hat of number theories and try to think about them as some kind of modular forms, modular functions. But he said they're kind of modular and they're similar to of so-called false theta functions, which were available, and he wanted to call them mock theta functions. Nowadays, we know how they're placed, where they're placed, and they carry a name of mock modular forms. So the definition, due to Zweigers and developed and also understood from many different perspectives by a number of people here, is that mock modular form is not quite modular. It's holomorphic. It has exactly the properties we saw before. But if you correct it by some error term that involves a normal modular form and makes our original object non-holomorphic, then it becomes truly modular in the usual sense. So that's the modern definition, again, due to Zweigers. And now this is a very rich subject, and it's amazingly interesting. It quickly brings us to the forefront of the study of such very special functions. And here I show one of the books written on this topic by Ken Ono and various collaborators. And in fact, last fall, we had a program with Ken Ono on various aspects of these mock modular forms and their applications, which include all kinds of amusing applications, including the one to vertex algebras. So usual modular forms or modular objects often appear as characters of infinite dimensional algebras and fall under the traditional definition given by Borchards, but the slightly more exotic modular objects can be often found in slightly more exotic infinite dimensional algebras. So just around the same time, Zweigers was making revolution in the, or mini revolution in this theory of mock modular forms, Katz and Wakimoto revisited their work from 80s, where they studied Lie superalgebras, and they found in 2001 paper, which quickly became very popular and pursued by many other people, mock modular forms, exactly of the kind that we saw before, and various cousins such as Appeler sums and so on, as characters of infinite dimensional algebras. And this is one of the applications or uses of such interesting types of modularity that you can find in the end of this book by Brinkman, Folsom, Ono, and Rokhlin. So I'll come back to this in a second, but now we learned something about our example. So we learned that not only it's interesting from the viewpoint of topology, but it's also interesting from the viewpoint of just as a function of Q. It's not quite a textbook material, but, and hopefully will be in textbooks on mock and other modular forms soon. But what it illustrates is that even the simplest example, such as this surgery on figure 8 or trefoil or plumbing graph with 4 vertices, gives us already one of the examples of Ramanujan. And trust me, once the reason I show this example and not something more complicated is even if I picked a slightly bigger example of this plumbing graph, I would be immediately outside of Ramanujan's mock modular forms, and I wouldn't know what name to associate to this function. So from the point of view of what kind of function of Q this is, it already, even the set of this plumbing graphs, table of integrals labeled by graphs, gives us amazing arena to play with. And even the smallest ones, the simplest ones, are already quite interesting, and it's pretty much at the cutting edge of what we can do. So what about this phenomenon of going from upper half plane to lower half plane in terms of tau, or from inside of the unit disk to outside of the unit disk with respect to variable Q? Well, this phenomenon generalizes, and here is a theorem plus conjecture. So I'm going to explain what this is in a second. And first of all, it's expected that this is true for any of this Z hat labeled by 3 manifolds. When you have a pair, 3 manifold and minus that 3 manifold with a reverse orientation, the relation is always going to be like this. But this is pretty hard to show, and pretty much the only class of examples where you can show this are examples of such plumbing graphs with only one trivalent vertex and no other vertices of valency more than 2. So if you think about these integrals, you can quickly, even from the definition I gave, see that really the complexity here of these integrals is controlled by a number of vertices which have valency more than 2. So three-valent, this star-shaped vertex with only 3 legs is the simplest class. And the generalization of the condition of negative definite that I alluded to before, but I can now formalize, is that the eigenvalue or matrix element of inverse matrix Q at the slot associated to this trivalent vertex should be negative. It's only one condition. So even if our graph of the type shown here has hundreds of vertices, we don't care about all this entire matrix to be negative definite. So the condition weakly negative definite only cares about one entry, namely the one associated to this trivalent vertex. If that's the case, under this hypothesis, one can show that this function defines so-called quantum modular form of weight 1/2. So this statement is a close cousin of what's written here, and it's a theorem. It's a theorem that you can find in the first 2 papers shown here, and it uses previous results of Lawrence, Zagier, and others. And this statement is not quite about series and Q. It's actually about, it's a statement about irrational numbers on a real line in the tau plane. Whereas what we really want here is a more specific version of the statement relating Q series or function of tau in upper half and lower half plane. And the way it's written here with more specificity, this is actually a conjecture which has been verified in 39 cases. 39 because there is a special class of this Rademacher sums that have to do with moonshine phenomena and so on, where you can actually prove it. But otherwise, this is a conjecture. So again, I just want to illustrate with this. If you're starting to get lost, indeed, I'm getting a little bit more technical since this is definitely past my first half of the talk. Takeaway is that from topology point of view, this is very little. But from the viewpoint, if you now approach this from the point of view, what kind of function of Q this is a lot. And this is basically all I can say at the moment. From the vertex algebra point of view, we're in a slightly intermediate position in the sense that here one can actually prove a theorem that for all of these manifolds, not just 39, but all of them, these are actually characters of also slightly more interesting and exotic vertex algebras called logarithmic vertex algebras. Just like mock modular forms, they don't play by the usual traditional rules, axioms of Borchards, but there are deviations of this which become very interesting pretty much around early 2000s, same time that these deviations from traditional modularity are being explored. And it just happens that this class of examples provides very specific characters of these logarithmic vertex algebras. And in fact, this is the way to understand some of the statements I mentioned earlier. So many of them become less surprising if you look at it from such perspective. And of course, it's expected that this is true in general. So we looked at this class of functions, this table of integrals that I introduced for you from several perspectives. From topology point of view, they provide invariants of 3 manifolds valued in Q series with integer coefficients, and this is good for solving this problem posed by Crane and Frankel 25 years ago. As function of Q, they also provide something interesting, namely they provide characters of exotic vertex algebras, infinite dimensional algebras, which are also at the cutting edge of what we're trying to understand in that area. And I hope, even though with this short expository presentation, I managed to convey that making progress in one field will actually help understanding what to do and how to proceed in another field. And also, we can try to rephrase challenges in one area as questions in the other. And that's how, by applying techniques and taking methods across the borders, we can actually now try to advance both of them together or several of them together. So as promised, in the last 10 minutes of my talk, I want to become quite more technical and return to this question about the role of this dependence on additional labels B, which from the viewpoint of three-manifold, there are as many of them as elements in H1 with integer coefficients, or better yet, spin C structures. And that's what I want to discuss in the remaining 10 minutes, because this is, again, quite surprising. And in my opinion, one of the most interesting aspects of the story, which was not expected, at least not by me when this came about. So first of all, as I mentioned several times, spin C structures and elements of H1 are in isomorphism with each other, but this isomorphism is not canonical. However, it becomes canonical once you choose a spin structure on a three-manifold. And one way to understand this is that there is a canonical map from choice of spin structures and elements of H1 into spin C of that three-manifold. Another way to say this, which is how it's often presented, is that choice of spin C structures form a torsor over H1. So this map will be useful to me in a minute, and there are many other interesting facts that you can learn from various books on spin C structures or that use them. And one particular subject that typically involves them is gauge theory, and in particular theory of Seiberg-Witten equation. So here is one of the good books on the subject that I highly recommend by John Morgan that gives a very complete and nice account and nice introduction into this. So let me try to argue that we should have actually anticipated appearance of spin C structures in this question in this topic. Even from what we knew about homological invariance of knots. Various knot homologies, such as Hovanov homology, Hovanov-Rosansky homology for high rank, or knot-Floer homology for rank 0, that's GL11 case, do not stand as independent theories. They exhibit many relations, which now can be understood via connections, for example, to Homfley homology. And there are many spectral sequences where Homfley PT homology is the first page, and these theories appear as infinity page. So there are many connections between these theories. One of these theories, namely in rank 0, the knot-Floer homology, to which the red arrow points, has actually analog for the three manifolds. The other theories don't, and I want to emphasize that what we're trying to ask in this question by Crane and Frankel is three manifold analog of Hovanov homology, which again doesn't exist, and so far none of this exists except for HFK. So three manifold analog of that is the Higard-Floer homology, and that does require a choice of spin C structures. This theory, developed by Oswald and Szabo, has counterparts based on gauge theory due to Kronheimer and Mrówka, same Seiberg-Witten equations as in the book of John Morgan, or via symplectic world of embedded contact homology developed by Mike Hutchings, which largely relies on work of Taubes. So I don't have to tell you in this audience that Klee famously proved the relation between Gromov invariance and Seiberg-Witten invariance, and this embedded contact homology is basically a three-manifold homology version of that relation. Each of these theories comes in 4 flavors, and there are all equivalent, including all of the 4 flavors, but that's not so important to me. What is important is that all 4 actually do require a choice of spin C structure in a very natural way. And therefore, even though that's not the theory that's counterpart of Hovanov homology, I want to ponder that if such homological invariance for 3 manifolds exhibit similar spectral sequences as what we have for knots and links, then we should not be surprised to see appearance of spin C structure in my talk. So once we're talking about Higard-Floer homology, I want to point out that this work of Oswald and Szabo led to very useful invariance of 3 manifolds, also labeled by spin C structures, of course, called correction terms. This basically represent homological degrees of certain terms in their complex. And these invariants, which are numerical invariants, these are just degrees, are extremely subtle and useful. For instance, they can provide completely new proofs of Donaldson's delegalization theorem and Tom conjecture about the genus of surface embedded in CP2. So here is an example of how this correction terms look like for length space. Length space LP1 has p different choices of spin C structures, and these are some fractional numbers, as you can see. Now, once we talk about spectral sequences and Hilgert-Fleur homology, there is another place which can provide motivation for appearance of spin C structure in my talk. Like I mentioned, we don't know Hovanov homology for knots and links and general three manifolds, but we know at least one example, namely knots and links in a solid torus. This is called annular or sutured annular Hovanov homology. And this is good enough to see that even from this perspective, spin C structure should appear. Why? Because this homology is actually triply graded. Usual Hovanov homology is doubly graded. It has homological grading and Q grading called quantum grading, but this one also has annular grading. And I want to argue, or at least in this subject, it's reasonably well known and understood that this is basically playing the role of spin C structure. In particular, there is a spectral sequence analogous to what I showed earlier, which starts with this annular Hovanov homology and converges to Hilgert-Fleur version, very similar to spectral sequences studied earlier by Oswald and Szabo. In this case, they were studied by Roberts, Grisby, and Worley. And under the spectral sequence, this third grading, the annular grading in the world of annular Hovanov homology goes into spin C structure. So that's again a very concrete illustration from the simple class of examples of knots and links in solid torus in thickened annulus that tell us that indeed we should have expected for general three manifolds labels that are valued in spin C structures. And finally, I want to point out that there are several other consistency relations, and even if we try to take our surgery formula with Cyprian and take this two solid tori from annular Hovanov homology, glue them together, we actually get exactly this set of Z-hat invariants I showed you before, or even their categorification if we want to venture that way. So then once, if I convince you that spin C structures are reasonably natural for as labels of these Z-hat invariants, and if I had more time, this would deserve perhaps yet another talk of its own. But anyway, if we're convinced that this is the right choice of labels, natural question then is to not try to sum over them as we did in trying to recover quantum group invariants. Remember, in that case, we had to sum over spin C structures when we took Q to root of unity. But what would happen if we don't? Can we find connection to other invariants of three manifolds labeled by spin structures or spin C structures? And this is where the name of Rokhlin comes into the title of my talk, because Rokhlin invariants of three manifolds are labeled by spin structures. And the correction terms that I showed you a moment ago based on Hilgert-Fleur theory are labeled by spin C structures. And indeed, you find connection between the Z-hats and such invariants if you take limiting values to either Q equals 0, for example, this overall power of Q, which was fractional, is basically a correction term. And if you take Q to I, fourth root of unity, you find precisely Rokhlin invariants of three manifolds. So not summing over spin C structures is also a good thing. And hopefully now it explains the title of the talk, because as a Q series, when we expand near Q equals 0, it provides interesting function of Q. That's where Ramanujan comes in. If we take a limiting value to Q equals I, we recover Rokhlin invariants and various other interesting invariants. And this function of Q interpolates between them, and Q, of course, is the Q of a quantum group. So what I did in this hour is actually barely scratch the surface, and I managed to explain, hopefully, or at least convey a glimpse of where this table of integrals could be useful. Part of it is topology, part of it is interesting phenomena related to modularity of characters of vertex algebras, which are also at the cutting edge. of that area. But I didn't say anything about where this invariance actually came from. You could have asked me, where did I get this table of integrals? I had to choose very special integrand in the first place to see that invariance and so on. And interestingly, it came from a numerative invariance, and I didn't say anything about it. And if I had more time, I would love to talk more about gauge theory and discuss various other questions. For instance, you can think about this invariance in terms of certain algebraic geometry of a fine Grossmanian that showed up in our recent work with Nakajima, Poshen, Sanyuk Park, Dupay, and my student Nikita Sapenko. There are many other interesting questions that are worth exploring here, and there are many other ways of building three manifolds. For instance, just like Hilbert-Fourier homologies built using cutting and gluing along higher genus surfaces. What I showed you today only involves cutting and gluing along genus 1. So obvious question is to extend it to Hilbert splittings and such more general cutting and gluing. From the point of view of vertex algebras or what kind of function is this, I try to emphasize that all we know is basically the surface of a tip of the iceberg where three manifold is defined by a graph with only one trivalent vertex. So in a very nice paper by Catherine Brinkman, Karl Marburg, and Anton Milic, they try to ask next question, what would happen for a graph which has two trivalent vertices? And they quickly get in a territory of higher depth mock modular objects, which are even much less explored. So this very quickly gets us in a territory of very interesting vertex algebras and Q-series invariants. So more recently, we're exploring connections to lattice integrable models with Boris Fagin, Kolya Reshetykhin. And again, there are many, many directions to be discussed here. So I want to finish with this broader message that it's really just a particular instance of interaction between this many fields. And this is the aspect that I find most exciting. Thank you.
Well, thank you, Sergei. We haven't really figured out how to give a round of thunderous applause here on Zoom, but maybe we don't have to much longer. Anyway, are there any questions while we still have a little bit of time? I think there were a lot of questions at the beginning anyway during the talk.
Well, I'll throw out a question. So what part of the original motivation was to categorify the Witten, Reshetykhin, Tareyev invariants, and I'm not sure what happened to that, to the answer to that question.
Yeah, to me personally, this was it was definitely part of the original motivation, and still is. So I'll be completely honest, 3 years ago, I knew nothing about logarithmic vertex algebras. So the fact that this turned out to be characters of logarithmic vertex algebras and were interesting to people in this other field made it only more exciting. But I come from a walk of life where I was interested mostly in this applications to topology. But and indeed, that's the problem that we're trying to solve since roughly early 2000s with Kumran Baffa and various other collaborators at various points joined and left. This was a very long-going program for about 10 years where we struggled, and it was trying to base things on work on categorification of knot invariants, which was quickly getting understood and developed, but we had a lot of difficulty of getting it off the ground until roughly 2016, when many of the surprising elements came in. But after that, the story developed pretty quickly, and that was very much motivated by the goal of connecting the world of enumerative invariants with quantum group invariants and their categorification.
What I didn't quite get is there at the end of the day a way to express a WRT invariant as an Euler characteristic?
Well, not at this stage, definitely. I would, from the way I presented it today, I would say that the way I picture it is first, WRT invariants are realized as not only limits of Q goes to root of unity, but also sums over this Q series. And now this Q series invariants have to be categorified. That would be my perspective.
I see.
It would be interesting to compare it to other approaches. For instance, I mentioned briefly this high representation theory pursued by Raphael Rouquet and homological algebra approach pursued by Belikov, Khovanov, and others, which work directly at the root of unity. So there could be various perspectives on it, I think.
Thank you.
All right, are there any further questions? Well, let's thank Sergei again. Thank you, everybody, for coming.
Yeah, thank you for coming. Hope everyone stays safe.